Hello everyone, in this lecture we are going to learn about Mdmt Calculations. Our flagship courses are Master Static Equipment Design and PVE Light, ASME Section 8 Division 2, and Master Welded Storage Tank, as per API 650. We have curated courses to suit your learning needs, so do visit our learning platform for more details on scutoid.thinkific.com. To know more about our comprehensive course and one-day workshop, register with a Learn More link in the description below.
So the topic for today, Mdmt calculation. So if you want to calculate Mdmt, the first step is to know what exactly Mdmt is. Okay. See, if you are defining Mdmt, there are two different types of Mdmt. Okay. So first you have to know whether we are talking about which Mdmt. So can you give me the two types of Mdmt? Then the definition will make sense. There are two Mdmts. One is service Mdmt and the second one is material Mdmt. Now your definition will make sense, okay? That it is the minimum possible service temperature. If I'm defining it like that, what exactly I'm defining? Service Mdmt or material Mdmt? It's a service Mdmt. Okay, because we are talking about service, what exactly will be required because of service? The reason may be different. Lots of different reasons are there. We'll talk about them. So, service Mdmt is the minimum possible temperature during the service. Okay. What is material Mdmt? Can you define in one sentence what exactly do we mean by material Mdmt? Service is what normally we relate when we talk about Mdmt. Okay. So maximum definitions which we got. Okay. So lowest temperature material is designed to. Material withstand for that. So it's related to the material. Okay. Service requirement, like this is the required thing. Now, whether my material is able to meet that requirement or not, that is the material Mdmt. Making sense? It's like this is the design pressure for which your vessel has to be designed. Now, how much pressure my pressure vessel can withstand? That is a different thing. Are you able to differentiate the service Mdmt and material Mdmt? Service Mdmt is what is the requirement of the service. Okay. How much minimum metal temperature is expected during the service. Okay. So let us take one example. That service requirement. My client wants that service needs to happen at minus 30 degrees Celsius. This is the requirement of client. This is the service Mdmt. Why it is there? We'll talk about that. What is the reason of service Mdmt? We'll talk about that. Okay. So service Mdmt is minus 30. When if client is asking that this is the temperature at which I need the operation to happen. Okay. Now, when we as a mechanical, see the client may be your process department, right? It may be internal or external, right? It is not like every time the external client will give you. Okay. So service Mdmt. Now, as a mechanical department, as a mechanical engineer, now we will design a system, design a pressure vessel, which should be able to withstand this minus 30 degrees Celsius. Means at minus 30 degrees Celsius, it should remain ductile. Okay. So that we will try to make sure. So we'll try to find the material Mdmt, whatever thickness we have and whatever is the material which we are using. So we'll find the material Mdmt. Now, if my material Mdmt is lower than the service, that means my material will remain ductile at that service temperature. So we have two different phenomena, material MDMT, which we will be calculating as a mechanical design engineer. Service MDMT will be given by the client. It may be internal or external. Okay. How many of you think that the arrow which I have indicated that is wrong? I'm saying material MDMT has to be less than service temperature. Is that correct? My material MDMT has to be less than the service. Okay. Now let us try to define. Okay. So hope you got a very simple definition of MDMT. Don't try to get a definition kind of thing because it does not make sense. If you remember in terms of example, service MDMT by client, material MDMT is what we have to calculate. The code gives methodology to calculate material MDMT, not service MDMT, right? Make sense? In code, whatever methods you have, that is for calculation of material MDMT, right? So hope it makes sense to everyone now. Okay. Great. So minimum design metal temperature is two types, service MDMT and material MDMT. Okay. Now let us tackle one by one both of these and we'll try to discuss the reason behind them. Okay. So service MDMT. What do you think might be the reason behind service MDMT? Like if my client is saying that the temperature during that operation may go down to minus 30 degrees Celsius. What do you think might be the reason behind that? Cold atmospheric temperature, because if the site condition is cold, then if the vessel is not having that operating temperature, it may drop to cold environment. Okay, so that is one reason. So every one of you has given. Now, endothermic reaction, depressurization. So now the service MDMT, the first reason is definitely service. If your service itself is at very low temperature, then definitely the metal temperature will go down, isn't it? So the first reason is my service itself is at very low temperature. Okay. So cryogenic service. If the service itself is very low temperature, then definitely that material temperature will go down because of service. So that is the first reason. Second, that is the site condition. If my site is in Russia, then definitely my temperature may go down to minus, okay, minus 30, minus 40 also. Okay. So two reasons. Now the third is very important, which is depressurization. Okay. And most of the time, 90% of the time, this is the reason for you to having a low MDMT. Okay. So depressurization is nothing but releasing the pressure with a very fast rate. If any item is pressurized, you are now relieving the pressure with a very high rate. Okay. So PV divided by T. Okay. So that is the equation. So if in very simple terms, if we suddenly depressurize any vessel, okay, so that is called depressurization. Now, what happens in depressurization? In depressurization, because of the change in pressure, okay, your temperature drops drastically. The temperature of the surrounding drops drastically. Now, why that happens? Let us consider as a LPG, okay, which is filled. Okay. Now, LPG is in liquid state, okay, and it is pressurized. Okay. Once you release the pressure, okay, when the gas is becoming from liquid to gas, okay, it absorbs lots of energy in that process. Okay. So there are two reasons which happens together. One is because of the absorption of energy, which is called latent heat, because of the phase transfer. And the second is PV divided by T is equal to constant. Okay, PV is equal to nRT. So because of the change in pressure, pressure is reducing. Okay. So your temperature also drops. Okay. So the temperature is dropping very quickly, and you might notice a formation of ice surrounding this gas. Okay. So if we are considering a LPG cylinder, you will see the accumulation of ice. Why? Because of the cold surface, whatever vapor particles are there in the atmosphere, they'll accumulate first, and then they'll, because of the very low temperature, they will form ice. Okay. So that is the depressurization. Is it making sense? So PV divided by T is equal to constant. That is the reason. Okay. The main reason behind that. Okay. And also the latent heat which is absorbed. Okay. So because of the change in pressure, and which is very sudden. Okay. If it happens very slowly, then this formation will not happen because that heat will be dissipated in the atmosphere, right? So if it is happening very sudden, then it is not getting time to transfer all the heat. So basically from surrounding to the cylinder, it is not happening because it's the cooling down with a very fast rate. Okay. Now, few might have already seen that phenomena occurring. So now you'll ask that why we are talking about this phenomena in pressure vessel. Okay. When it can happen? Is that possible that whatever pressure we have maintained in a pressure vessel, suddenly it is getting depressurized? It can happen because of an offset condition. What that offset condition may be? Maybe a pressure safety valve has opened up. Okay. And it will suddenly depressurize, leakage. Okay. That is also one. So any leakage happening, and the leakage is big enough, which is having a very good rate of loss. So in that case, your depressurization will happen. Okay. So now how to find the temperature which is achieved because of that? That is done by client, and client, I mean process department. Okay. So process department, when at the end of the formation of your PNID, and when they are ready for HAJOP, that time basically the study is done, which is called depressurization study. In that, they locate the walls which are there, which may open up and may allow the liquid to flow and may allow to depressurize. So what will be the effect of that on your pressure vessel? So that study is done, and based on that you get the service MDMT. And this is the most of the time reason for you having lower MDMT. Okay. And also the reason for hold written behind MDMT. How many of you have noticed that most of the time in the process data sheet, you will find hold after MDMT? Most of the time when you are starting a project, you will be finding hold written all the time when process is giving you the data in the start of the project. Okay. When they are still not done the depressurization activity till that time, because in the start you cannot do depressurization activity. Okay. Once every system is finalized, then at the end they do this. Okay. And that is the reason till the time they have not done depressurization, they are not in position to give you the service MDMT. Make sense now? So that is the another reason for having a temperature which is very low and calling for a negative service MDMT. Now, material MDMT is what we find. Okay. So we calculate material MDMT based on code, which we are going to see today. Okay. That is the agenda for today, MDMT calculation. So when we are talking MDMT calculation, we mean to calculate material MDMT, not service MDMT. Okay. So if you compare, now can you give me the relation? Material MDMT is equal, greater, or less? Which sign? Material MDMT is equal, greater, or less? So maybe less. Normally we don't make it equal. We always try to keep it less. Okay. So material MDMT has to be lower than service MDMT. Now, many times we get confused that what exactly should happen. Okay. Now, if you just take a very simple example, again, a very similar example which we took. So minus 30 degrees Celsius is my service MDMT. Okay. Now, what you want? Do you want a ductile material at this temperature or you want a brittle material? What you want? You want your material to remain ductile at this temperature? Yes, obviously. Then my material MDMT has to be like minus 40 degrees Celsius. That means till minus 40, it will remain ductile. So if till minus 40, it is ductile, then I can use it. Right? If it is not, then I won't be able to use it. If it is only having minus 20 degrees Celsius as material MDMT, can I use it for minus 30? No. Right? Because material will become brittle at minus 30, which I don't want. Okay. So just a simple extension of what exactly you're thinking will help you to decide what exactly is the relation between these two. Okay. So we'll talk about impact testing also. Okay. So when we do impact testing, when this condition exists, like, you calculated MDMT and you got minus 20 degrees Celsius, while service is minus 30 degrees Celsius, then by material MDMT, you cannot decide whether the material is still ductile or brittle. So only thing which can give you guarantee is doing impact testing. So you'll do impact testing and you'll decide whether it's suitable for that temperature or not. Okay, so that is a separate thing. Here we are trying to calculate the material MDMT and know the methods, what exactly is given in code for that. Okay. So the first step will be to go to UG20F. Okay. So my step 1 is to go to UG20F and then we'll try to do some calculation. So it's not calculation, but just understanding of the code. Okay. So Jafar, you are absolutely right that starting will be always with the calculation of the governing thickness. Okay. So if you want to call that as a first step, you are absolutely right. That first will be calculating the governing thickness, okay, which is very important. And then first clause in ASME code, which talks about whether I can get the exemption from impact testing or not. Okay. So that statement reads like this. Impact testing as per UG 84 is not mandatory for pressure vessels that satisfy all the conditions. Now, what are those conditions? First one, material shall be limited to P number 1, group number 1 or 2. That is the first condition. Okay. And in that, thickness not exceed 13 mm for curve A and 25 mm for curve B, C, and D. Okay. So if you read like this, it may look a little bit confusing for people who have not referred. So let us take one example. Okay. 516 grade 70. Okay. If it is not normalized, what do you think is the curve for that? What is the curve for that? Curve B, right? Now, many of you might be wondering from where this curve is coming. So we'll talk about that also. very shortly. But till now, just assume that it's curve B. So 516 grade 70 will fall into curve B. Okay. Now let us assume that my thickness is 20 mm. I have calculated the thickness. I have the material. Okay. Now, is it fulfilling the first condition? 20 mm 516 grade 70 material. Is it satisfying the first condition? Yes, it is satisfying. Okay. It is less than 25 mm. Okay. So first condition is satisfied. What is the next one? Vessel is hydrostatically tested, which we do most of the time, right? Most of the time we'll be doing the hydrostatically tested. Very rarely we'll be doing pneumatic or proof testing is almost negligible when we talk about pressure vessels. Very, very few. Okay. So hydrostatically tested 99% of the time. So it will be yes. Third, your design temperature has to be within minus 29 to 345. Okay. Now, third condition, I cannot satisfy by just having this information that my thickness is 20 mm and material is 516 grade 70. Okay. So I need service temperature. What exactly is required by the client? So if client is saying service MDMT is minus 25 degrees Celsius. Okay, that is given by the client. So service MDMT minus 25. My material is 20 mm thick and it is SA 516 grade 70. So is the third condition also satisfied? Is the third condition satisfied? 20 mm thickness, 516. So first condition, hydrostatically, most of the time we do. So yes. And minus 25 is the service, okay, which is falling between this temperature. Okay. So third also satisfied. Now fourth one, no shock or cyclic loading. Okay. If there is a cyclic loading, in that case, these exemptions cannot be taken. Okay. So now these are the four conditions, right? 1, 2, 3, and 4. So if all of the four conditions, if all of four are met, then you can take the exemption. Okay. You don't need to perform impact testing as per UG 84. Okay. What if any one of it is not followed? Let us see, there is a shock load or cyclic load. Siddhar is asking what is shock load. Shock load is like suddenly you are inserting a fluid which is at very high temperature or a very high pressure, and it is happening multiple times. So shock loading may be in terms of pressure. It may also be present in terms of temperature. So sudden rise of temperature or pressure, that is your shock load. Okay. Cyclic loading, most of you might be already familiar. It's a variation of pressure and temperature or either of it. Okay. So it will be varying from plus minus some values. So varying in terms of cycle. Okay. So that is called cyclic loading. So if that is present, okay, then can I take the exemption as per UG 20F? If any one of it is not satisfied, can I take the exemption? Can I take the exemption if any one of it is not getting satisfied? Anyone. You won't be able to take that exemption. Okay. So now my next question, listen to it very carefully. Is that mean if it is not meeting, let us see this condition was not satisfied. Is that mean that I need to perform impact testing? Is that mean I need to perform impact testing? No. then you have to read this statement which is given here as it is not mandatory to go for UG 84. Okay. So that means exemption is not permitted by this clause, but may be permitted by other. Okay. So if it is not meeting, does not mean that you need to go for UG 84 and do the impact testing. Okay. So there may be other clauses which may provide some exemption. So many places you may have the condition, but as per code, there is nothing. Now, based on services, based on the conditions, you may end up doing impact testing, right? So let me take one example that will maybe able to clarify it to everyone. Okay, so examples are best way to see that. Okay, so that is the reason I've kept examples also. So let us take one example. So that will clarify the doubts of everyone. So I'm taking 516 grade 70. Material is not normalized. It is having 20 thickness and minus 25 degrees Celsius. Okay. All other UG20F conditions like hydrostat testing minus 29 to 345 as a design temperature and no cyclic or shock loading. Everything is satisfied. Can I take that exemption? That we have already discussed. Okay. So for this, how you'll be doing the checking? You'll be writing all the conditions. Okay. So first, P number 1, group number 1 or 2. So 516 grade 70 falls into P number 1, group number 1 or 2. So this condition with thickness 20 and here you need less than 25. So can I say that first condition is satisfied? Yeah. So if my material 516 is P number group number 1 and the thickness is less than 25, so that condition is satisfied for the example which we have taken. Okay. So we'll say, yes, it is satisfied. Now we'll go to second one. If first one is satisfied, then only I can go to second one. If first one is not satisfied, then I'll stop there itself. Okay. And I'll look for other clauses which may give some relaxation. Hydrostatically tested. So we are assuming that every vessel is hydrostatically tested. So yes, this case is also acceptable. Third, 345. That curve for P number 1, group number 1 is either B or D, based on normalized or not normalized. So all B, C, and D all falls into the B, C, D category. So second one, which is 25 thickness. Okay. So design temperature is minus 25. So this condition is also meeting. Thermal or shock load is not present. Okay. So this condition also is meeting. Okay. So can I take that exemption? What do you think? Can I take that exemption of impact testing in this case? Yes. So simple. Now let us try to take another example. Example 2. Again, the 516 grade 70 is not normalized. Okay, the material is not normalized. So curve B. Okay. Required thickness 32. Nominal thickness 36. And service MDMT is minus 32. Can I take that exemption from UG20F? Both thickness and the temperature, both are exceeding. Okay. So here I cannot have more than 25 thickness and service MDMT, I cannot go lower. Okay. If my thickness would have been 20 still I'll not be able to take that exemption because service MDMT is minus 32. It is beyond that limit which gives the exemption by UG20F. Make sense? So I think most of you have responded very correctly. So great. So if you just run the case for this one, we'll be able to know that we cannot take the exemption. Okay. So now if we are not able to take that exemption from UG 20F, that does not mean we have to perform impact testing. It means we can look for other clauses. What is the next clause which can give us some exemption if it is not, we are not able to get that exemption by 20F? We'll go to UCS 66, okay, for a carbon steel and low alloy steel material. So we'll go to UCS 66 and there you will find the curves which are mentioned. Okay, the curves which we spoke earlier, curve A, curve B, curve C, curve D. So you'll find the definition of all the curve, like which material falls into which curve, you will find it here. Okay. So curve A, 216, the fittings which are normalized. Okay. 105, forced condition. Okay. If it is 105 normalized, then it will go to curve B. Okay. So curve B, 216 normalized, okay. Grade WCA, then 285, and then 516 if it is not normalized. Okay. So you can see the different curves here, A, B, C, and D. Now one question. Listen to that question very carefully. If I increase the thickness, the increase in thickness either means MDMT increases or MDMT reduces, or it remains same. By increasing thickness of a material, MDMT increases, it reduces, or will remain same. What is the relation between thickness and MDMT? If you are confused, just see the curve which is in front of you. The relation is already there. Okay. So most of you responded very accurately. Few of you are confused. So if I take one example, if I have a 40 mm thick, okay, and let us see curve B is applicable. Okay, my material is 516 grade 70, which is not normalized. So what is the MDMT? Can you read the MDMT value for 40 mm? So 12 degrees Celsius, right? Now, can you give me the value for 80? If my thickness is 80 mm, then what will be the MDMT value? 26 around, right? 26 or 27. Okay. If you want exact, then you can refer the table also. Tables are also available. So you can refer that. But it is giving very much clear indication that by increasing the thickness, MDMT increases. By increasing the thickness, MDMT increases. So can I say it's inverse or directly proportional? By increasing the thickness, my MDMT is increasing. Okay, it's not inverse. Inverse is opposite. If my thickness is increasing and MDMT is reducing, that will be called as inversely. Okay. So here it is directly proportional. So increasing the thickness is increasing the MDMT. So higher the thickness, more MDMT problems you have. Okay. The chances are more that you'll end up doing impact testing. Okay. If the thicknesses are high. So remember this relation. Okay. Great. So we have seen two curves, curve A and curve B. Let us talk about curve C and curve D also. So curve C, 182 grade forgings, F1 and F22. If they are normalized, they'll fall into curve C. 516, grade 55 and 60, not normalized, will fall into curve C. Okay. In curve D, the thing which you have to remember is 516, any grades. If they are normalized, they will fall into curve D. Okay. So that is the definition of different curves. Okay. So normalize is a heat treatment. Okay. So we provide a heat treatment which increases the toughness property of a material. Okay. So it will give you better impact property. That is the normalization. It's a heat treatment type of it. Great. So now, based on UCS 66, let us see if we have understood. So let us take another example where my material is 516 grade 70. It is now normalized. So it will fall into curve D. The required thickness is 32, nominal thickness 36, and service MDMT minus 32. Okay. So based on configuration, first you'll be calculating the governing thickness. And in this case, let us assume that this 36 is your governing thickness. Okay. In that case, if 36 is my governing thickness, definitely I cannot take as exemptions from UG 20F. So I'll be going to UCS 66. Okay. I'll be applying that. Now, can you give me, by looking at the curve, what will be the MDMT value for 36 mm? For 36 mm, can you give me the MDMT value by looking at the curve? Approx value is also acceptable. Minus 27, minus 29. So roughly to that, right? So if we try to draw the curve, so minus 36 will lie somewhere here. Okay. And if we match with curve D, roughly we are getting as maybe, close to 27, minus 27, 28. Let us see what we have calculated. So minus 27 is what we have taken. So if you are actually calculating, will you take the graph or you will take the table values? What will you take for if actual calculation? You have to take table, right? Because here it may be varying with some point. So if you want to actually calculate, please take the table. So minus 27 is what we have got as the material MDMT. Now, can I take that exemption by using UCS 66? Can I take that exemption? I got the material MDMT as minus 27. My requirement was minus 32. Can I take that exemption? Governing thickness is the minimum thickness of the welded parts. In a very short definition, if I tell you, there's a very long definition of that. There are lots of things which are involved. But in short, if I have welded a component, this is the thickness of a component, and it is getting welded with a lower thickness. Okay. So the governing thickness here will be the lowest thickness which we are welding. So that is the definition of the governing thickness. Now, once we have calculated, now can I get that exemption? No. For taking that exemption, I need material MDMT less than the service MDMT, right? So here minus 27 is definitely not less than minus 32. So this condition is not satisfied. And for that reason, impact testing is not exempted. Now, what does that mean? Do I need to go and do impact testing? What should be my next step? Doing impact testing? We will not go and do impact testing. We have another clauses which may give us some more relaxation. Okay. So first we'll go to UCS 66B, which is nothing but figure UCS 66.1. Okay. So that clause provides a reduction in MDMT. So whatever we have calculated, if we can take some further reduction. Okay. So how much reduction we can give. That is what this clause is providing. Now, what is the basis for the taking the reduction? T required and nominal thickness, Tn. Okay, very good. So whatever extra thickness which we have provided, okay, so that consideration is provided in terms of reduction in MDMT. Okay? So whatever thickness you have selected, that is not the required thickness. Okay? You have provided extra. So code gives you exemption for that. Now, what exactly that is? That is what we call it as coincident ratio. Okay? What exactly is coincident ratio? It is nothing but the ratio of required thickness divided by the nominal thickness minus corrosion allowance. So corroded nominal thickness. Make sense? Like, no, you may think that, okay, see, I have used higher thickness than required. So in terms of MDMT, why I am getting the credit? If you are providing, okay, let us say 32 mm was required, you are providing 36 mm. So for pressure, definitely it's a margin. But for MDMT, you can say that the less is good, right? So if you are providing more, it is not beneficial, right? It will further worsen your MDMT. Does this question came in your mind anytime? So the thickness is more. More thickness is problematic for MDMT, isn't it? More thickness worsens your MDMT because we have just seen the relation. Higher thickness, it will increase your MDMT. So how come you are getting advantage of giving higher thickness? Is that question clear now? We take advantage, that is very clear, but how? In our mind, our normal logic says that higher thickness means problem. So it also depends upon the stress which is getting generated. Okay. So by having higher thickness, the stress which is generated inside the material is less. Okay. And for that reason, you are given that credit. Make sense now? So because the stress is lower, okay, by providing the higher thickness, okay, so you are getting advantage based on that. Great. So how you'll be calculating? So in this case, the example which we have taken, so TR was 32, TN nominal thickness 36 mm. Corrosion allowance, you can consider 3 mm, which is usual. So what coincident ratio I'll be getting? That in curve, MDMT increases because it purely talks about the thickness. It does not consider stress in that. For the same stress, if your thickness is increasing, then you'll be able to get advantage, not independent. Okay. So in the curve, it is not related to stress. Great. So uncorroded, it's TR divided by TN. So you get, yeah, TR is uncorroded. So 32 mm as the required thickness is always uncorroded, Sridhar. Okay. If you remember T required, T design, and T nominal. So design thicknesses with corrosion allowance, isn't it? Right. So 0.96. Now by using that coincident ratio, can you give me the reduction in MDMT? Using that curve which is there, left hand side, which is nothing but figure, you see a 66.1. So can you give me the value? So around 4. Okay, let us see. Let us try to draw that curve. So 0.96. Okay, so what was the value? 0.96, right? So here we have drawn, whatever we have drawn, that is, I think, not correct. So that drawn is at minus 0.9, which is not correct. It should be roughly here. So at this location. Okay. So if I follow this location, then something like, if I draw with a straight line, let me just draw that with a straight line. So roughly we can say it will be 3 to 4. Okay. So 3 or 4 will be the reduction in this case for 0.96. If it is 0.9, then it will be definitely more. What will be for 0.9? Maybe roughly equal to 7. Okay. 6, 7, 8. 6 or 7, roughly that. Okay. Great. So now, so if we consider 6 degrees Celsius, because we have taken 6, which is not correct, by the way, because that orange curve has to be a little bit up. Okay. So if we consider 6 degrees Celsius, then it will be minus 33. But if it is in this case, it will be minus 4. So in that case, it will be only up to minus 31. So if it is minus 31, so the actual value which you see here will be 4 degrees Celsius. And this also minus, sorry, this also will be 4. So this will give you minus 31. So is it exempted? By using 66.1, I have gone till step 3, but still not exempted. Okay. Then, do I have anything additional? Yes. See, whatever T required you have. Okay. So T required, let us see, I have 14.7 as my T required. So T design will be 3 mm addition, so 17.7. Okay. And then you decide the nominal thickness based on that. Okay. So whatever is the corrosion lines, that is affecting both. Okay. So your TN is getting added, and then finally you are reducing that 3 mm and getting the 15. Okay. If corrosion allowance is, let us say, 5 mm, then you'll be rounding up based on 19.7, so 20. And again, you'll do minus 5, so 15. Getting that? So that is the calculation. Yeah. So see, some of the client may, if they're writing in the specifications, the client may always make it more stringent. Okay. It cannot relax the requirement. Okay. So if client is saying not to take advantage of 66.1, you cannot take that. Okay. So, in this case, we are not able to get that exemption. Okay. Anything else is left for us? Any other clause? 68C. So if this is the case which we have taken, okay, and we got, so what exactly 68C says? That when PWST is not a mandatory requirement. Okay. For a case where PWST is not a mandatory requirement, can you give me when that will not be a mandatory requirement as per UCS requirement? At which thickness PWST is not mandatory? 38, right? So between 32 to 36, by doing preheat, we can manage. Okay. But above 38, it has to be done, right? So above 38, the PWST becomes mandatory. Less than 38, we can get that exemption by doing preheating. Okay. So if my thickness is 36 mm, material is 516 grade 70, is it mandatory to do PWST? Is it mandatory in this case to do PWST? No, right? So if it is not mandatory, but still I am doing PWST, even though it was not required, but still we are doing. Now, what can be that case? Okay. So when can you tell me a case where this may be a possibility that even though it is not required as per thickness, but it is required because of the service, like because of service requirement. Okay. So if it's lethal service or sore service, you may end up doing even amine service, you may end up doing PWST. Okay. Or maybe client is asking for PWST. That also may be possible. Okay. And maybe based on all these factors. So lethal service, sore or amine. Okay. So if it is a mandatory requirement and you are doing, okay, so in that case, you will be able to take that advantage of reduction in temperature. How much reduction in temperature? 17 degrees Celsius. How much reduction? 17 degrees Celsius. So can you tell me what exactly is my new MDMT, material MDMT? So before you do the subtraction, give me the value in which you will be doing the subtraction. Whether you will be doing the subtraction in UCS 66 value or 66.1. In 66, what we got? We had got minus 27. And when we applied 66.1, we got minus 31. Right? So which one? If PWST is not required, but either by any of the reasons, by client or because of service, if you are doing, then exemption is permitted. Okay. So not mandatory by means of UCS 56 by thickness. Okay. Apart from that, if you are doing, you can take that exemption. So now again, coming back to the question, which reduction you'll be using, which temperature? Minus 27, which you got from UCS 66 or by 66.1. Which one? Which one will give you the... So whenever you are applying 68C, you will be using UCS 66 value. You cannot use the coincident ratio reduction. Okay. So you always take this 27, whatever you have got based on UCS 66. That will form the basis of the reduction. Make sense to everyone? So remember that many times we do the calculation wrongly. MDMT calculation, one is 68B3. What exactly this is? Can you read this statement and tell me what exactly it means? This zone which you see, which is hashed, okay, what does it mean? The hashed portion. What do you mean by that? Why it is there? So when that ratio which you calculated by using TR divided by TL, actual thickness is very high. That means if your ratio is less than 0.35, in that case, your MDMT will be directly minus 105. So you can use that up to minus 105. So up to minus 105, you can use that item if you are having stress ratio as minus stress ratio as 0.35 or less. Okay. So if you are having very high thickness, that means your stresses are very low in the component. So code is giving you permission to use it at very, very low temperature. Okay. So these are the only options when you can go less than minus 48. So if you read UCS 66, so code makes a statement that you cannot go or take that exemption below minus 48 degrees Celsius. But excluding these points, it mentions that excluding this. So this will still be applicable. Okay, make sense? Sridhar will take that. So is it making sense, guys? Is this statement making sense to all of you? 68B3, which talks about the coincident ratio going less than 0.35. Your MDMT reduction is available up to minus 105. So you can go up to that. So that is a very good point which we have. One more thing is left. Can you tell me what exactly that is? Minus 48 is the temperature below which you cannot go in the normal scenario. You cannot take that exemption below minus 48 bar. Make sense? So you already the clause is written, Aman. 68B3. Just read that. See, UCS, AV, we are talking about UCS. So can it be independent of material? It's for carbon, steel, and low elastic. So we are talking about the requirement of carbon and low elastic, not for every type of material. Yes, correct. Yeah, great. So one more thing is left, which is 68B1 minus B. Okay. Again, related to coincident ratio. Okay. Now, if you have a flange, let us say a standard flange, you are not calculating the thickness for that, right? How you will be able to calculate the coincident ratio for that? This question should come into your mind, right? If I'm using a standard flange, okay, or a flange, normal flange, where the thickness is not calculated, but the stresses are calculated. Okay. And based on the stresses, thickness is determined. So how you will be able to calculate the ratio, the required thickness and nominal thickness. Okay. So for that, okay, for all the like flatheads, okay, where the stress pattern is not tensile, but bending. Cover also, you have bending stresses which are governing. Tube sheet also same. Okay. For all these items, okay, you have one more method which is available, which is maximum design pressure at the MDMT temperature divided by MAP, maximum allowable pressure at MDMT. This ratio will work as coincident ratio. Okay. So if I have a standard flange, then maximum design pressure divided by the rating which you have got, okay, by the normal selection. That will give you the coincident ratio. Okay. So for all these items, you have additional method available which you can use, okay, for getting that coincident ratio. Is that make sense? Flange is exempted up to minus 29 directly. You are right. But whether all the kind, is that all the kind of flanges are exempted up to minus 29? So whether every kind of flange is so fine grained, okay, which will happen because of normalization. So in that minus 29, otherwise minus 18, right, will be applicable. Great. So that is it. We have planned a one-day workshop, and now this may be even useful for the paid members who are already learning. So one day, a quick recap of many basic things which you can have. So one day workshop in ASME Section 8 Division 1. The duration of that will be one day event. It's online and live, like what we are doing right now. You will be having one workbook with you. We'll be sharing one workbook where you can note down. So whatever you're learning, that will be very much systematic in that workshop. And also you'll be sharing one coupon worth 7,999 in that workshop, which you can utilize for yourself, or you can share with anyone whom you think this course might be useful. So talking about the content, what exactly we'll be covering. So we'll be covering mainly the basics part. So basics of pressure, temperature, and stresses, which is very much important. And any one of you who might have gone through that pressure, temperature, and stresses. Okay. So you might have noticed how much depth we have covered in that. So material specification, section 2, part A and D, how to read that. Okay. And then introduction to ASME Section 8 Division 1, which will talk about lots of chapters, like basic configuration, how that ASME Section 8 Division 1 is structured. So we'll talk about that in the intro. And then the forward, which is very much important for everyone. Before reading the code, you should read the forward. And then we'll talk about scope and U2G. Then UG16E. If many of you were confused that whether we have to do the calculation in corroded or uncorroded. Ahmad will talk about that. Just hold on. So, Karthik, if you are a paid member, then everything whatever we have covered, that is already available, okay, for paid members in a recorded, manner. So don't worry. So UG27 and MAWP and MAP, the difference between design pressure, MAWP and MAP. You learn in such a way that you'll never forget the differentiation. Okay. So we'll close by 5, and this is what we'll be covering.
Elevate your engineering expertise with our comprehensive ASME Section 8, Division 1 course. Enroll now to master static equipment and PV Elite course, and ensure your success in the industry. To know more about our comprehensive course and one-day workshop, register with the Learn More link in the description below.